you can also do integration by parts for definite integrals. It's the same story, but you have a and b here and here, and here and here. So here you plug in. It's the same story here. I mean, exactly the same. One function gets integrated in both spots. The other one stays the same here, but is differentiated in the new integral. The hope when you apply IBP is that it's going to be possible and that the new integral is going to be easier to deal with than the old one. Right, so here's a practical example. Find the definite integral from 0 to 1 of 11 plus 6x e to the power 2x. So we can just chop it up. 1 is going to be very easy. And here you need to use integration by parts. So as an area interpretation, this is going to be 11, right? 1 times 11. But let's do it algebraically. And here you use integration by parts. So as before, we will let ux be 6x, and then d prime x has got to be e to the power 2x, and so dx is e to the power 2x over 2. And let's write that on the side like that. So we have the square brackets 1 and 0, and here we have ux times dx minus the integral from 0 to 1 of vx times the derivative of u. And here this one is nice, because now there is no annoying x. So you get 11 minus 0. Before I plug in things 0 and 1, I'm just going to tidy up the function into which I'm going to plug stuff. And here the new one is so simple that we can immediately think backwards. Don't forget to always find an antiderivative to your integrand before you plug in the limits of integration. Anyway, 11 plus 3 times e to the power of 2 minus 0 minus all, note the brackets please, of 3 halves times e to the power of 2 minus 3 halves times e to the power of 0, which is 1. But anyway, so we get 11 plus 3e squared minus 3 halves e squared plus 3 halves. So this comes out as 12.5 plus 1.5 e squared. Two improper integrals, we investigate whether they converge or diverge. The first one we treat in the ABC manner. So first we look at the proper version. Remember, we don't like denominators, so we integrate from 1 to b. You can think of b as being some very large but still fixed number. So this is what you get. So the integral from 1 to b of our function 10 over x squared is 10 minus 10 over b. Whatever b is, be it a million or a trillion or 10 trillion. And so to get the improper one, you take the limit of the integral from 1 to b as b tends to infinity, but whatever b is, this guy is equal to 10 minus 10 over b. And here it's 10 minus 0 as you let b go to infinity, so it's 10, so it converges. In the second one, this one doesn't look so nice to, I mean, you don't want to think backwards here really. There's a much simpler way, and that's the sandwich argument. So you need a bottom and a top, so we sandwich our function, the integrand. So 0 is going to be the bottom. The 1000 is just a number, so who cares? This works because x squared plus 3x is bigger than x squared in the interval of integration. So since the integral from 1 to infinity of 1000 over x squared dx is convergent, because it's 100 times this one in part 1. By comparison, the given improper integral in part 2 converges. This word problem comes down to a simple differential equation. At noon, Peter has driven 7 miles and his speed t hours after noon is 25 plus t miles per hour. The question is, how far has he driven in total at 2 o'clock in the afternoon? Okay, so we want to introduce a function. Let ft denote the number of miles Peter has driven at time t hours after noon, because obviously if we knew ft as a function, we could just plug in 2 and find f of 2. Alright, so how can we use the given information to get the information in a mathematical sense about ft? Okay, we have a differential equation because we know his speed at time t. Speed is the rate of change of distance, and hence it's described by the derivative of a distance function. So f prime t, the derivative of our function, of our distance function, is 25 plus t. That's the differential equation. And then we also have an initial condition, because we know that f of 0 is 7. So now you can solve it. First, you look at the differential equation. Forget about the initial condition for the moment. So, to go from the derivative to a function, you need to integrate. Because integration is like differentiation backwards. So ft must be 25t plus t squared over 2 plus c for some c, for some constant c. And then we use the initial condition to determine what c is for us. So f of 0, if you plug in 0, you get 0 plus c. That's supposed to be 7. So that implies that c is 7, and hence, all in all, ft, the distance function, is 25t plus t squared over 2 plus 7. Because by the differential equation, ft had to be 25t plus t squared over 2 plus c for some constant c, and then the initial condition was used to determine that c must be 7. And so ft is 25t plus t squared over 2 plus 7. Now, obviously, in particular, f2 is 50 plus 2 plus 7, which is 59. So, answer, 59 miles.